Summary of an Introduction to the Standard Model of Particle Physics. The book provides a detailed introduction to the Standard Model of Particle Physics, covering fundamental interactions, particles, and mathematical frameworks. The focus lies on the electromagnetic, weak, and strong interactions among quarks and leptons, as well as the unifying framework that ties these forces together. The text includes both theoretical foundations and experimental validations, making it a comprehensive resource for graduate students and researchers in particle physics. The particle physicist's view of nature. The opening chapter introduces the elementary particles and fundamental forces. The Standard Model is built on the concept that the universe consists of quarks and leptons interacting through gauge fields. The theory relies heavily on quantum mechanics and special relativity, incorporating symmetry principles to describe the interactions. It begins with electromagnetism and extends to the weak and strong forces. The chapter also discusses the gravitational field, but excludes it from the Standard Model due to its negligible influence at the particle level. Lorentz transformations. Lorentz transformations are critical for the Standard Model as they ensure that physical laws are consistent in different inertial frames. The chapter covers rotations, boosts, and proper Lorentz transformations, introducing scalar, contravariant, and covariant vectors. Lorentz invariance is a core principle that guides the formulation of relativistic quantum field theories in particle physics. Lagrangian mechanics. The chapter elaborates on Lagrangian mechanics as the theoretical foundation of the Standard Model. Using Hamilton's principle, the equations of motion are derived from a Lagrangian density. Continuous systems are described, leading to the field equations that form the basis for quantum field theories. The Klein-Gordon equation for scalar fields and the concept of the energy-momentum tensor are introduced to describe fields and interactions in a relativistically invariant manner. Classical electromagnetism. Classical electromagnetism sets the stage for understanding quantum electrodynamics. The Maxwell equations are introduced, along with their formulation in terms of a Lagrangian density. The chapter emphasizes gauge invariance, which later becomes crucial in the formulation of the Standard Model. Space inversion, charge conjugation, and the intrinsic angular momentum of the photon are explored to establish foundational concepts for later discussions on gauge bosons. The Dirac equation and quantum fields. The Dirac equation describes fermions, such as electrons and quarks, which are fundamental to the Standard Model. These chapters cover the solution to the Dirac equation, the introduction of spinors, and Lorentz invariance in the context of spin 1/2 particles. Additionally, gauge interactions between fermions and bosons are discussed, establishing the mathematical framework for QED and electroweak theory. The idea of negative energy solutions leads to the concept of antiparticles, a pivotal feature in particle physics. Quantizing fields and QED. Quantization of fields is essential for developing quantum electrodynamics, which describes electromagnetic interactions at the quantum level. The chapter explains the canonical quantization of boson and fermion fields and introduces renormalization, a technique used to address infinities arising in quantum field theories. The success of QED is highlighted by its accurate prediction of the electron's anomalous magnetic moment, reinforcing the validity of perturbative methods in quantum field theory. Symmetry breaking and the electroweak theory. Symmetry breaking is a critical concept in the Standard Model, particularly for explaining the mass of the W and Z bosons in electroweak theory. These chapters discuss the Higgs mechanism, where local symmetry breaking introduces the Higgs field and explains how particles acquire mass. The Weinberg-Salom theory, uniting electromagnetism and the weak force, is also introduced here. This section covers lepton interactions with the W plus minus sign and Z bosons, charge conservation, and CP symmetry. tests of the Standard Model and strong interactions. The validation of the Standard Model through experimental results is a key focus of these chapters. The discovery of the W plus minus sign and Z bosons confirmed the theory's predictions. The study of quark interactions is detailed under quantum chromodynamics, which explains the strong force symmetry such as isospin and chiral symmetry, and the confinement of quarks within hadrons are presented, alongside lattice QCD, a computational tool used to simulate strong interactions. Neutrino physics and beyond neutrino masses and mixing phenomena are explored, introducing the MSW effect and neutrino oscillations, which were crucial developments after the initial formulation of the Standard Model. The discussion extends to major antineutrinos, sterile neutrinos, and the possibility of physics beyond the Standard Model. The book incorporates neutrino mass into the Standard Model and addresses ongoing experimental research that might reveal new particles or interactions. Anomalies and the future of the Standard Model. The final chapters delve into anomalies, specifically the Adler-Bell-Jacques anomaly, and its implications for the Standard Model. The cancellation of anomalies in electroweak currents is necessary to ensure the theory's internal consistency. The epilogue discusses the ongoing research at facilities like the Large Hadron Collider, which seeks to uncover new physics and potentially extend the Standard Model to incorporate gravity and other unresolved questions in particle physics.